this tutorial we're going to discuss a very useful algorithm called the Oct Tree algorithm. So as you recall, in a previous tutorial we discussed an algorithm called the regular fallacy algorithm, and this is a root finder algorithm. So if you have a function which is positive on one side of the root and negative on the other side of the root, then the regular fallacy will help you find this zero crossing. A very similar one-dimensional algorithm that achieves the same goal is called the bisection method. And the bisection method, it also finds the root. However, instead of looking at the secant line, it just bisects the region of interest recursively. So let's say this is our initial region of interest. So if we were to bisect the first time, then this would be the average of our initial limits, and then we can check the signs of the function. So if it is the same sign here and here, then we know that there's probably no zero on this side of the bisection. But if the signs are different, then we bisect again, and we keep bisecting until we either converge or we find or we reach the limit of bisections. So after, let's say, 8 or 10 bisections, we can be pretty confident about the location of a zero. So if you want to extend this idea to 2 dimensions, then you have to use another algorithm called the Oct Tree algorithm. Oct Tree algorithm. And in this case, the idea is very similar. So if you have a 2-dimensional region of interest, and you have a function which is positive on one side and negative on another side, then you would subdivide the initial region of interest into 4 subregions. And then you can check the corners, or if you want to be more precise, you can check the edges as well. And if the sign is the same, then you know that we don't need to subdivide this any further. But if the signs are different, like in these 3 subregions, then we know that we need to subdivide it further. So let's say we subdivide this one further. And then once again we have a region which doesn't have any zero crossing, and all the signs are the same. So we can ignore this region. Okay, so let me show you an example. So the Oct Tree implementation here. And as you can see, this is the same pattern as I showed you here. So we see that we have positive region here and a negative region here, and then also another negative region here. And we only subdivide when we know that there is a zero crossing inside the subregion. Okay, so let me show you. Okay, so if you want to extend this idea to 3 dimensions, then there's another algorithm called the Oct Tree algorithm. which essentially does the same thing, except you have a cube or a box of interest initially, and you subdivide it into 8 subregions. So let me show an example. Okay, so this is the same example as the same gear example, the same gear function as before, except that we have a three-dimensional gear function which also has a top and bottom. So let's see. Let's run the script here. Okay, so as you can see, this is the same gear, except it's a three-dimensional version. And basically, the function that generated this is positive inside of the gear and negative everywhere else, and it's just the distance function. So it's a signed distance function. So if the point is outside of a gear, then the distance is positive. If the point is inside of the gear, or sorry, I guess it's backwards. But it doesn't really matter what the sign is as long as there's a sign change. Okay. So if we look at the actual function here, so that's the function here. So these angles are used to do the little gear teeth. So you can see here we have 18 gear teeth on the big circle, and then we have 8 gear teeth on the small circle. So it's an 18 to 8 conversion. And these are our top and bottom faces. Yeah, so that's basically it. And of course you can 3D print these if you have the mesh. So if you can generate a mesh for the isosurface, then you can 3D print it. Okay, so let's see what else we have here. So we can also run another function. Which I think is pretty neat. So this is a cube, and basically you just subtract a sphere from it. So you can do set operations with these functions as well. So you can compute the minimum or sorry, the union or the intersection of different functions. And the way you do that is by using maximum and minimum functions. So if we look at this cube minus sphere function here, then we see that we're just finding the maximum distance. This is our maximum distance from all of the cube faces. So this m gives us the distance away from the cube, and r gives us the distance away from a sphere. But since it's negative, then that just means that we're subtracting the sphere from the cube. And of course, you can print this guy as well. So here's the printed out result, which is pretty neat. Okay, well, basically that's it. That's the end of the tutorial.